Hello and welcome back. Serious summation. More double series. I don't know if you remember the 2m plus n that I did a while back now on for year 13 further maths enrichment. This is the souped version, and I'm going to do a little bit of a discussion because this is not quite the same. This is actually targeting mostly undergrads that have seen perhaps a little bit of first year 3D calculus, that like double integration, because the ideas behind it are very, very similar. But that's not to say you will not be able to follow what is going on if you haven't done this. But it's definitely enrichment. It's definitely a 5-star question. I haven't decided. I wrote the question a couple of days ago, so I haven't decided where I'm going to place it, in what section, if any. So let's have a think how we're going to approach this. What is different about this particular double series? The problem is this: from n is equal to m to 19, and from m is equal to 1 to 19. The question is, what does that even mean? I mean, n is equal to m and then to 19. So the dummy variable, of course, is n, and m is a constant, so we can actually split it. It can be done. It's going to be a bit of a pain and a bit of a twisting your brain around to actually see what you need to be doing. It's definitely doable, but for something like this, probably we need to reverse the order of summation. So like for those who are obviously at degree level, they know how to reverse the order of integration, double or triple integrals. So we need to somehow run the dummy variable n on the outer and the dummy variable m on the inner. For something like this, there are some shortcuts which I don't want to discuss it in here. It can be done literally in 5 seconds if you see it before, but this does not make sense much. So it's best to do it the long way, which of course it shares ideas with integration. So I'm going to draw a picture up here to guide us with this particular question. So this is a graph, and this is not an xy plane, it's an nm plane if you want. And the nm plane is not a continuous plane. So for example, there's no such thing as a 1.7. It's only 1, 2, 3. It's discrete. So first of all, I'm going to look at n is equal to m. Is the line, of course, like the line y is equal to x, which runs diagonally. So that's m is equal to n. And I need to go to n is equal to 19. N is equal to 19. I'm looking at this integral here. Not integral, so I said integral, but it's the same ideas, believe it or not. 19 there. So that's going to be 1, 2, 3, all the way up to 19. And of course, it's only this point that is there. There's nothing in between. So these points do exist on the line, but nothing in between, okay? And that's the point 19 up there. And do I need to make this a little bit longer perhaps? Because I cannot really map it there. That's my 19 there in M. So make a bit more room. So that's your M axis again. Somewhere here is your 19. And then it's of course 1, 2, 3, all the way up to 19. And as I said, it's only discrete values of integer values that are there. So n is equal to m is this line here, and I need to go up to n is equal to 19, and then I need to go from m is equal to 1 to 19. So what does that mean? This doesn't actually take any place for the time being. Please ignore that. From n is equal to m, so I need to add things from that start on the line n is equal to m. So somewhere here, let's say on this, I'll start there. So I'm going to add things that start from n is equal to m and go all the way up to n is equal to 19. So dot 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 all the way up to 19. So that's what this sigma says. And then once I've done a row like this, could have been here, of course, it could have been there, it doesn't really matter. Add all such rows from m is equal to 1. There's your m axis. So add all the rows which look like this. And there's another one here. all the way up to m is equal to 19. That's what the outer integral is saying. So clearly, all I need to do is to somehow count all of these points, if you want, on the MN plane that have whole numbers as the coordinates. What about this particular one? You can think of that as this is the point, for example, 3, 2 there. That's this point here, 3, 2. What do I know about this particular point? When I reach that point, what I will be actually attributing to this is 2 times is m, which is his y coordinate, 2 times 2, plus his n coordinate, which is plus 3. So that will be adding to my sum, to my total sum, 7, if I see it from this picture. But of course, I need to somehow formulate it differently when I go to my sigmas. So this is what is happening up there. Just explaining again very, very quickly this time. I'm going to add things from the line n is equal to m, so along some kind of horizontal line from n is equal to m to n is equal to 19 inner integral, and then sum all of these rows starting from m is equal to 1 all the way up to 19. So I will be adding all of these quantities. So now I need to reverse this. So now that I know what my points are, I need to reverse the summation. So I'm going to start with m is equal and n is equal. So if I'm looking in m now, it's still the same points I need to account for. I need to add points that start from m is equal to 1, and I'm looking at, let's say, a random column now, from m is equal to 1 until I get to the last point up here, which is m is equal to n. And then I will need to add all the columns from n is equal to 1, I'm looking on the horizontal now, from n is equal to 1, 2, 3, all the way to 19. Now this makes more sense. You might think, okay, is there a lot of difference in all of this? The answer is yes, it is, because I'm starting with 1 at the bottom, which is hugely important. Okay, from this line now, I can start my evaluation, which is not difficult at all. Outer sum, I keep saying integral because, of course, this is to do with integration, really. That's my second, the inner integral now. I'm going to split it as 2 lots of sum from m is equal to 1 to m is equal to n. I don't actually need m is equal to n. Of course, the bottom determines which one is the dummy variable, 2n if you want. And that's my m in there. And the second sum is going to be from m is equal to 1 to n again, but now we have an n. This n here, I'm going to write it, but I'm going to instantly remove it from there because, of course, this n, the summation is in m, so we can pull it outside. It's a constant and put there 1. We begin the summation. That is 19. N is equal to 1. We're inside here. 2 times. We're adding whole numbers from m is equal to 1 to n using the standard formula. I'm going to write underneath it is a half n plus 1, and to that we will need to add, we're adding ones basically from 1 to n, so it's going to be n, that's this n on the outside, times n, which of course will give me n squared. The formula that I'm using up there is, of course, sigma r squared, r is equal to 1, no, r squared, r, sorry, to n is a half n plus 1, which is a well-known formula. Okay, we tidy from there. So just a little bit of algebra, which is not difficult. Of course, this will cancel. We're going to have n squared plus another n squared, 2n squared. N squared plus n squared, 2n squared. And I'm also going to have another plus n. And from this line now is all standard results from A level, really. I think these formulas for sum of squares and sums of cubes and sums of integers are given in formula booklets. I'm going to go to the top so I don't have to bend down. This is going to be 2 lots sigma n is equal to 1 to 19 of n squared plus another sigma n to 1 to 19, and that's going to give me the sum of squares, I believe, is 1/6 n plus 1 to n plus 1. So it's going to be, let me just write it, sum of n squared is, if we summing, let's say from n to k, is 1/6 k plus 1 to k plus 1. So in our case this is 19, so it's going to be times 19 times 20, 2 lots of 19, 38, 39. We can use a calculator, I don't have one at the moment, sorry. Plus this is now a half n or k or whatever you want to call it is 19 times 19 times 20. And oh gosh, try to simplify that without a calculator now. Is going to be 1/3, and 1/3 of 39 is 13. 13 times 19 times 20, that's this bit here, plus a half times 19 times 20. Factorize 19 times 20 out, because I'm too lazy to grab a calculator. 13 plus a half. Okay, use a 2 from the 20, change that into a 10, so it makes 26, 27. So all of this now will be 270 times 19. So 270 times 19 will give me 5,400. Take away 270, so that'll give me an answer of 5130, I hope. And of course you can check it with a calculator in your own time. I hope this made sense, changing the order of summation. I did my best to explain it. I haven't taught this for a very long time, and I'm a little bit rusty. Maybe my explanation could have been a little bit better. Maybe I'll do another video in the future to explain it in a little bit more detail. And who's laughing now? We certainly are. I think we are much better in series now.